So we just looked at, and we were looking at number 41, that graph that had this kind of a behavior and then came up and came to a horizontal tangent, but then decided to continue to go up. Okay, I want to talk about that spot right there. Okay, that spot where the graph comes to that and has to make a decision. At that point, the graph has to be like, okay, what am I going to do here? I'm at a point of horizontal tangency. Okay, am I going to change my direction or not? So this particular function, I'm making it, what do they call that in English, where you give an inanimate object like it does personification? Okay, I'm giving this personification. Okay, so the function is deciding at that point, do I change my direction or do I continue? Okay, so this function decides to continue to go up, but something changes. Okay, can you see that something changed about that function? Okay, the curvature of the function changed. We've got a function that's curved in this way. And then what changed, even though it's still going in an upward direction, the curvature changes. Okay, the vocabulary word for that is called concavity. Okay, the point at which that happens is called a point of inflection. In English, the vocabulary word inflection, like we use that to talk about how your voice changes. You know, when guys are going through puberty, it's like, ooh, and that little voice crack. Okay, or if somebody is speaking, what's the opposite of speaking with lots of feeling? Monotone, right? Somebody who's just speaking like this. All right, but somebody who's speaking with inflection, their voice goes up when they're excited. Their voice might get quiet when they want to say something suspenseful. They're speaking with inflection. Okay, so inflection is the increase and the decrease. The point of inflection is what we call that in math. All right, and it's where the curvature, which we now call concavity, makes a distinct change from one to the other. All right, so here is just an example of something, a big satellite dish out, I think this one's in Australia, okay, that has particular concavity. This has concavity that's all the same. The curvature of this paraboloid, okay, there is its curvature. All right, and you can see that it's the beams that it's going to be either sending out or receiving are all coming in this way. And then they bounce off of the bottom and they all reflect into that focal point there. But there, it's like how it's receiving that. Okay, kind of like a bowl in that bowl shape. If you flipped that upside down, then that would have different concavity. We call this concave up. Okay, when the curvature, we say, oh, the function is concave up or the shape is concave up. Here's a function. A cubic is a classic function that has two different concavities. Okay, it changes from one type of concavity, which we say concave down, to another kind of concavity, which we call concave up. Okay, so concave down would be this, all these things would be emanating down from the curve, as opposed to concave up. These are all emanating in that direction, okay? And the point where that changes is called the point of inflection, and in this case it was the origin. Okay, we call that the inflection point or the point of inflection. And all of this is measured by the second derivative. So if the first derivative always measures the slope, the second derivative will always measure the concavity of a function. Okay? So in this particular cubic, the slope is always what kind of number? The slope is always positive. Okay, the slope is going up, 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 up. It's 0 for an instant, and then it continues to go up. So this is a positive first derivative. But the second derivative will show a significant change from one to the other, and that's going to happen at the origin. All right, so here's the vocabulary we're talking about on slide 18. All right, the graph of a differentiable function is considered concave up, and you can defend that in two ways. You can say that y prime is increasing itself. The derivative is increasing, or you can say the derivative of the derivative. So we say the derivative of the derivative is positive, so that's this. Okay, the derivative of the derivative is positive. That forms a concave up section. Or when the derivative of the derivative is negative, the second derivative, that would form a concave down section. All right, so here's some classic examples of functions whose concavity rapidly changes over and over and over again. Okay, you can have multiple points of inflection. So this one would be occurring about like that. So this first section, what would you classify that as? Concave up or down? Down, right. And then it changes to concave up until maybe that point. And then it changes back to concave down again until maybe about right there. And then it changes again to concave up. And then it changes again to concave down. And so every time as it's moving itself down, that particular graph, look at the points of inflection. What if you connected the dots? What would you have? A perfectly nice, straight, linear piece on that particular function. It's really pretty if you took the points of inflection and connected them. Okay, nothing, it's just interesting about that one. Okay, it happens the same thing with the other one, the one that's going with a positive slope. Okay, going through quadrants 1 and 3. The same thing would happen where that point of inflection just continually changed over and over again. Okay. Point of inflection, if you were to eyeball, okay, why don't you try it? Look at that bottom one. Eyeball where you think the point of inflection is. Okay, yeah, just put a dot on there where you think the concavity changed from one kind of concavity to another. If I were to eyeball it, I think I'd put mine about right here. I don't know about the rest of you, but that's where I would say that this had negative concavity. It was concave down. And then at that point is where it's going to switch. And then you can check your math, and if you check the second derivative. Right? The second derivative would be changing from one kind of number to the other and would be equal to 0 at that point of inflection. In terms of COVID, when we were talking about flattening the curve back in 2020, and our curve looked like this, and then it was going up, and then they wanted to go like this, they were all talking about that point right there. That was where the curve started to get flat. Okay, it's where it changes. It's where the curve is, up until that point, the slope is getting steeper and steeper and steeper and steeper. But at the point of inflection, from that point on, the slope started to be less and less and less and less. That's where the concavity changes, is when the slope stops getting steeper and starts to become more flat. That doesn't mean that the slope is totally changing direction. It just means it's less flat than it was before. Okay, the steepness has decreased. All right, so we've now defined that. The point at which the graph of a function has a tangent line and where the concavity changes is called the point of inflection. Okay, notice how many different kinds of tangent lines do we know about? 2. Okay, they are horizontal and vertical. It didn't specify. It could be either a horizontal tangent line or it could be a vertical tangent line. Okay, so like that one, like this, right here, what kind of a tangent line does it have? No, not horizontal. Vertical, right there, that moment. Okay, so it can have a vertical tangent line too, but the concavity is changing. The slope is not. The slope is positive, 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 positive slope the whole time. The concavity is what changed. All right, so let's practice. Find all the points of inflection for this cubic. How many points of inflection do you think a cubic's going to have, based on your knowledge of what a cubic looks like? Okay, yeah. You should kind of, I can picture a cubic, and it's going to have one point of inflection, but let's find it mathematically. So we're going to blitz through the first derivative. So 6x squared minus 28x plus 22. And we'll go right to the second derivative. So 12x minus 28. Set that equal to 0. So x is 28 divided by 12, which when we reduce, that's 7 over 3. Now that's not enough to be a point of inflection. All I know right there is that the second derivative is equal to 0. The only way that you prove the point of inflection is to make another second derivative chart around 7/3, and make sure you're checking the second derivative value. So pick me a number less than 7/3.
0.
Great. Check 0 in the second derivative, so y double prime. If we check 0 in y double prime, what kind of a number will we get? Negative. All right, and then pick a number that's clearly bigger than 7/3. 10. Okay, 120 minus 28, that's clearly a positive number. That is the part that's necessary to show that it's a point of inflection. You cannot just say it's a point of inflection because the second derivative is equal to 0. The word change has to be in every reason that you do, just like with the first derivative test. It is a point of inflection not only because the first derivative is, or the second derivative is equal to 0, but because the second derivative is also exhibiting a change. Now, the nice thing is, you don't have to worry about the changing from plus to minus or minus to plus, because it's just a point of inflection either way. There's not different kinds of points of inflection like we have maxes and mins. It's just one kind of point of inflection. Okay, find all the points of inflection for sine. Okay, based on your knowledge of sine, how many points of inflection are there? Okay, there are infinitely many points of inflection because we know that sine looks like this and it just keeps changing. Wow, that's a really poor sine graph, but okay, it keeps changing its concavity over and over again. I could say, okay, it's going to be here and 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 all infinitely. I don't have to do the calculus to know that the points of inflection are changing. In fact, I can just use my basic knowledge of I know when those are. All of those points are happening on the x-axis every time the sine graph crossed the x-axis, which is going to be pi, and it's going to be again at 2 pi, and it's going to be again at 3 pi and 4 pi. So you can use your common sense, but you can also prove it mathematically. So we go through the first derivative, which is cos x. We go to the second derivative, which is the negative sine of x. I set that equal to 0, and that still solves with plus or minus k pi, where k is an integer. Every whole value of pi is going to be a point of inflection, even starting at 0 pi, even all the negatives. So I would need to check the second derivative, something less than, and you pick an arbitrary pi value. Let's pick something less than pi, and then something greater than pi. And we just have to show that there is a change in the second derivative. So if I pick something smaller than pi, say 5 pi 6 or something. Okay, 0 is too far because 0 is already one of those numbers. It has to be something you can't go too far. You got to, because it's all 0 and pi, so it has to be something close enough. Pi halves would be fine. Okay, but remember, you're checking it in the second derivative. So if I picked pi halves and I put that in, I'm going to get a negative number, which should correspond to the fact I know that this has negative concavity. The shape of that is a dome that's upside down, so it has negative concavity. Then maybe 3 pi halves, and that turns out to be a positive number, which matches what I know about the shape of that part of sine. All right, find all the points of inflection for x squared. Okay, well, what do you know about x squared? It's a parabola. What about the shape of x? What kind of concavity does that have? Positive concavity. Will that ever change?
No.
Okay, so I know that there should be none because the concavity never changes. But can I prove that mathematically? Okay, well, we're going to blitz through the first derivative. We get 2x. We'll go to the second derivative. We get 2. We try and set that equal to 0. Which is not, and so I've confirmed mathematically what I knew to be true, that a parabola with a minimum at 0, 0 has no change in its concavity. Its concavity remains the same throughout the whole time. Sometimes I think of concavity as like, could I fill this with, sand or water or something? That's also another way to think about it. That's concave up. All right, how about this one? Maybe not quite so intuitive. Find all the points of inflection for the graph 2e to the negative x squared. Okay, so maybe not so much. I don't really know how that's all going to go. Okay, so, but we have to trust. If the math was good for the other stuff, the math has to be good for this one too. So we'll go through our first derivative. All right, how do I take the derivative of that? Okay, got to remember our exponentials. So the rule is 2e to the negative x squared. But then something else comes after that. Times Lenny times negative 2x, which is going to clean up to be negative 4x times e to the negative x squared, and then Lenny is 1. That's the first derivative. Okay, let's find the second derivative. Okay, the second derivative is going to require me to do what kind of rule? Product. So we'll start with e to the negative x squared, and then what will be the next part? Negative 4 plus negative 4x, and then times that derivative, which is e to the negative x squared times Lenny times negative 2x. So if I clean this up, now switch it to numerator and denominator. Okay, what is in the numerator? Negative 4. What's in the denominator? E to the positive x squared instead of negative. All right, plus, what's in this numerator? I don't think it's negative. Pretty sure it's going to be positive 8x what? Squared. Okay, and then Lenny is 1, and then what's my denominator?
E to the x squared.
Right, so we call those common denominators. So we have e to the x squared, and then 8x squared minus 4 is my numerator. So I've done the math. Now what do I need to do with that second derivative? Set equals 0, and what else? Right. Both of those processes. So we're doing it with the second derivative this time. So we'll take 8x squared minus 4 over e to the x squared and set that equal to 0 over 1. We'll also take 8x squared minus 4 over e to the x squared and set that equal to 1 over 0. And we'll do the cross multiplication on that. So when I solve this, what will x be equal to? X squared would be equal to plus or minus 1/2. So plus or minus the square root of 1/2. Okay, what about cross multiplying the other way? I'm going to get e to the x squared equals 0, which is not possible for any e to ever be equal to 0. If you know what e looks like as a graph, you know that e gets really close to 0, but it's not ever going to be equal to it. Yeah?
Why did we set the earlier ones to 1 over 0?
If we were finding maxes and mins, we would.
Okay.
Oh, you mean these ones back here?
Yeah.
Because there was no denominator for any of them. So we should have, but there was no denominator, so we would have gotten circle with a line through it for every single time.
Okay.
So I was kind of rushing through that. All right, so we've got 2 of those. Now, is that enough to prove that they're points of inflection? No. Okay, I need to check whether or not they are points of inflection. So x less than the negative square root of 1/2, and then between the negative square root of 1/2 and the positive square root of 1/2, and then greater than the positive square root of 1/2. And I am checking the second derivative now. So don't mix those up. So what's something that would be clearly less than the negative square root of 1/2? Negative 2, negative 10, negative anything, all right? Let's pick something, and we're checking the second derivative. All right, so if I take a negative 10, say, and I put it in here, what will happen to it? Okay, I'm going to get a positive number, so the numerator will be, and then this will be clearly positive, because it's always going to be positive, so that would be a positive value, okay? Something clearly between these two. 0. Put 0 here. What's going to happen to the numerator? Negative, and the denominator is still positive. So that would be now a negative. So I've just shown the existence of a point of inflection because the second derivative changed. And then pick 100 or something, and then you're back to positive again. All right, last one. Find all the points of inflection for this. That's going to have a square root in it because of the half. Yeah.
Wait, sorry, how do you know e to the 0 is negative?
What's anything to the 0?
1.
Okay. So the numerator was negative, and the numerator was negative, and the denominator was 1.
Okay.
So the numerator was negative 4, the denominator is 1, so that'll be a negative number. All right, last thing. Find the points of inflection. So again, we're going to blitz past maxes and mins, but later we're going to put them all together. We're going to do all of everything, but for now we're just going to do maxes and skip maxes and mins, but we still have to do our first derivative. So our first derivative again is going to be product rule plus x to the half times 1. So there's my product rule. Always make it into numerator and denominator. It's going to make your math later so much better. So my numerator is going to have x plus 3. What will my denominator have in it? 2 root x. And so the other one would have what in its numerator? 1. And the denominator is just plain root x. So what do I need? Oh, excuse me. Root x and 1. There we go. Okay, so we need to multiply by 2 rad x.
Oh, that's it. Okay.
So I'm going to get a common denominator of 2 rad x, and my numerator, good, 3x plus 3. Now, if I was doing maxes and mins, I would take that and I would set it equal to 0 and 1 over 0. But for now, we're going to skip that part, and we're going to go to y prime, double prime. Okay, do you want to leave it like that to do y double prime? If you do, what rule will you need? You would need quotient rule. If you change it, then you can use the product rule if you want. So I would probably change it, and I would probably have 3x plus 3 times x to the negative half, and then I probably would divide both of these guys by 2 so that I had my 2 over there. That's what I would do. I think the math is on that going to be easier. Or, if you didn't like that, you could always write it like this, 1/2 x to the negative 1/2. You could do it that way too. Either way.
Why can't you just divide those ones by 2?
Why can't I?
Distribute it.
I'm distributing the half. Okay, so then we'll say, all right, 1/2 x to the negative half times 3 is the product rule. And then 3x plus 3 times, all right, what's the derivative going to be here? Negative what? I'm taking the derivative of this part now. So how do I take its derivative? Negative 1/4 x to the, what's the new power on that? Negative 3/2. Okay. So my numerator has a 3 and a 2x to the half. My other numerator has a negative and a 3x plus 3, and the denominator is going to have a 4 and an x to the 3/2. So how do I make that common? What do I need to multiply this by so that it looks like this?
Which is not
Oh, what do I multiply the 2 by?
2.
Okay, so I'm going to multiply by 2. All right, and then what do I multiply by to go from x to the half to make it x to the 3/2? Plain x. Because what do? you add the powers. Okay? So the rest is just algebra and then cross multiplying to find your points of inflection.
Oh.
Is that hurting your brain?
Yes.